right, so far we've talked about two different types of growth, and we're just going to compare them side by side to do a quick refresh on all of this. We got exponential or geometric growth. Let's see if we can find a pattern here in this table. What do I need to multiply to get from -2 to -4? I need to multiply -2 by 2. -4 times 2 is -8. 16 times 2 is -32. Remember, with exponential or geometric growth, we talk about the common ratio. So our common ratio in this case would be 2 because I am multiplying by 2 each time.
And then if we come over here to this side, we have a linear function or arithmetic. This is a new word that we're introducing today, and it means the same thing as linear, where we're growing by the same amount each time. If we look at this table here, if we start with 2, how much do we have to add to 2 to get to 6? Okay, we'll have to add 4, and then 6 plus 4 is 10. 14 plus 4 is 18. So here we can see that the common number that we're adding each time is a 4. Over here, we represented this as the common ratio with R, and with linear or arithmetic sequences or functions, we are going to represent it as D, or the common difference is going to be 4. We're talking about arithmetic and linear, we'll use D, common difference, for the number that we're adding or subtracting every time, and then for geometric and exponential, we'll use R, the number that we're multiplying by each time.
Let's check out what the graph would look like. We already know that an exponential graph kind of looks curved, but in this case, since it is in the negatives, it'll look a little different. So I go over 0, down -2, and then down, down. It's just going to double. And if we were to do our slope triangles, notice that our y values is going to be twice as tall every time. Right? This is, again, a rough sketch, but it'll get larger and larger by a factor of 2.
And then if we look at the graph here of this linear function, if we start here at 0, 2, we grow by 4, so 1, 6, rough sketch, we are going to have a linear line that represents this pattern.
What if we wanted to write an equation to describe this? There's two types of equations we can write. We're going to talk about recursive equations first. Let's talk about writing a recursive equation for this table here. So recursive means it's defined in the term that came before it. So if I look at my current term, for example, the fourth term in our list here is -32, or a sub 4 is -32. This term, the current term, came about because I took the term before it, the previous term, and in this case, I multiplied it by my common ratio, which is 2. I times it by my common ratio. We're going to turn this idea of my current term is the same as my previous term times by my ratio, which in this case is 2. We're going to turn this into algebraic terms. So my current term, instead of x and y, we're going to swap this out for f of n and n. This is more of what you'll see on derivative. So n, this is my nth term. And this is my function of n, right? This is my actual list of numbers for my sequence. So my current term is just my f of n, and that is equal to my previous term, which is f of n, but the one before. So it's n minus 1. That's how we write the previous term, times by r, because that was my common ratio. So this is the basic format for writing a recursive equation for an exponential function. However, I have to give a starting term, because if I just say f of n equals f of n minus 1 times 2. If I just give someone that, if Emma were to create a list, she could start anywhere, right? Like she's like, okay, I just take the number before and multiply it by 2. She could come up with a list of like 2, 4, 8, 16, 32. So she followed the instructions, right? She took the previous term and she multiplied it by 2, but our lists look different, right? -2, -4, -8, -16, -32. Our lists look different because we didn't start at the same spot. So we have to also give, with the recursive term, you have to give the equation, and you also have to give a starting value. It could be whatever. So I could give it as f of 0 equals -2. I could also give f of 1 equals -4. Like, it doesn't matter, but I have to give a starting term.
Taking the same idea that Tiana explained over here with writing a recursive function for a geometric or an exponential growth, we're going to do that over here with a linear or arithmetic growth. In previous videos, we have learned how to write an equation for a linear line, but we learned how to write an equation explicitly. And we will talk about the explicit form in the next video, but here we want to learn how can we write the arithmetic sequence recursively, and we're going to write it the same way here. We're going to take our current term, and then it's going to be equal to the previous term, but instead of times our common ratio, because we're not multiplying over here, we are going to add our common difference, so plus d. If we think of this in terms of our scenario here, we can say if we want to look at this term right here, okay? So this is our current term, and it's defined by our previous term, which is 10 plus d, and d is 4. So 10 plus 4 gives me 14. We'll now write this in algebraic terms. We will have our f of n, because we changed this from x and y to n and f of n. So this is our current term, and it's going to be equal to our previous term, which is f of n minus 1, just like it was over here. F of n minus 1 less d, our common difference. All right, and just like over here, we have to give some place to start, because if I just said that my equation was f of n equals f of n minus 1 plus d, I could start anywhere. I could start at 0, and I could say, okay, 0 plus 4 is 4. Plus 4 is 12, and I could keep going. And this technically fits that rule, but it does not match my table up here. So I have to give a place to start, and we will represent that the same way as we do with geometric, as f of something is equal to something. And we can pick whatever term we want. So a lot of times you'll be given f of 0 equals something, or f of 1 equals something. And this just allows us to know where our pattern starts so that we can continue with the same pattern that we have here. And we'll be able to have started on the same value.
Let's try writing a recursive equation. So we're given this table here, and we want to see, is this linear / arithmetic, or is this exponential / geometric? So looking at this, it doesn't look like it's decreasing at a steady rate. Jumps are too big. So let's see if we can figure out what our common ratio is. I can always figure out the common ratio by taking the larger term and dividing by the term right before it. So if I did 9 over 27, that would give me a common ratio. 9 over 27 is the same as 1/3. So my common ratio here is timesing by 1/3. All right, so if we remember our recursive form, when we take our current term, which we define as f of n, and that is the same as taking our previous term, f of n minus 1, and I'm being multiplied by 1/3 each time. To get our current term, we take the previous term, and we're multiplying it by 1/3. Get this term, I have to take the one before it, multiply by 1/3. I want to get my next term, the fourth term. To get this one, I'm going to have to take the one before, 9, and times it by 1/3. So that's the first part of a recursive equation. And then we also need to give it a starting value. So I could say f of 0 equals 243, and this would be my recursive equation.
If we look at this table example here, we start with 0 and 30, and then we go to 1, 22, 2, 14, 3, 6, and 4, -2. And we have to figure out what's happening. Are we multiplying by something every time? Are we subtracting, adding? Well, if we look at our first term, we can see that it is decreasing as we go on. So we know it's either being multiplied by some sort of fraction, or we are subtracting something every time. And if we look at the difference between these, 30 to 22 is -8. 22 to 14 is -8. We can clearly see we are subtracting the same number each time. So now let's try to write an equation for this linear or arithmetic sequence recursively. And so a recursive equation always starts with f of n, meaning the term that we're on, the current term, and that's going to be equal to the previous term, f of n minus 1. And then what is happening to our previous term? Subtracting 8. So we'll subtract 8 there. So our recursive form is f of n equals f of n minus 1, and then subtract 8, because every single time we're subtracting 8 to get the next term. And then we have to remember, we always have to include some term so we know where our sequence starts. Okay, so I could say f of 0 is equal to 30. I could say f of 1 is equal to 22. I could even say f of 4 is equal to -2. As long as I give some place so that I know where this starts, so that my sequence will be consisting of the same numbers. If we are given this recursive equation here, now our job is to see if we can figure out how to write the sequence. We'll say write the first 4 terms in the sequence. They already give us what f of 1 is, which is awesome. So we can start our sequence with -1, because we know that f of 1 equals -1. I know that my first term is -1, and if I look at my recursive equation, I can see that to get the term I want, I have to take my previous term and multiply it by 5. So I'll take my previous term, -1, multiply it by 5, and that gives me -5. If I want to find this term here, I'm going to take my previous term, which is -5, multiply it by 5, which will give me -25. So then to find this term, my fourth term, I will take my previous term, which is -25, multiply it by 5, which will give me -125.
All right, let's talk about writing the first few terms of a sequence given the recursive form. Sometimes you'll see it in terms of f of n, like in function notation, and sometimes you'll see it written in sequence notation, where it's a sub n minus 1. It's the same idea where this is the current term equals the previous term. In this case, I am subtracting 2. This is my common difference every time because I am subtracting 2. So a sub 1 is my first term, so my first term in my list is 1. And in order to get my next term, or my current term I'm on, I have to take the previous term, and I have to minus 2. So 1 minus 2 is negative 1. And then we can just continue the pattern, get my next number. I have to take the previous one, I have to minus 2. So just subtracting 2 every time gives me negative 3, and then we can just go from there.